Okay, today we're going to look at some applications of the electric force, and we're going to start with our first example of these parallel plates that can be used to accelerate a particle. So I have these parallel plates drawn here, and I'm going to have an electron come in and be accelerated through. So that immediately tells us some things regarding the charge density of these plates. Mainly, the charge would look like this, so that the field would look like this for an electron. Notice I drew the field for an electron. Field for a proton, or a positive charge, would look like this still, if you have a positive charge going in. So just make sure you realize that when I'm referring to a field, I'm referring to an electric field that's accelerating an electron. So the field does point like this blue up here, but we're interested in this white arrow because that's the direction that the electron's going to travel. It's going to speed up. So enough about the electron for right now. Let's talk about these parallel plates and the electric force. So we know that the electric force from a infinitely flat plane or sheet is 4k pi sigma, or 4 pi k sigma, whichever you prefer. You can shuffle them all up. And in this particular problem, we're going to be interested in what sigma is. That's what we're going to be looking for. And to help us find that, we have to go back and talk about the electron a little bit more. The electron, we know, has mass. That mass is 9.11 times 10 to the negative 31st kilograms. So it has very, very small mass. And in this case, it has a very large acceleration, 4 times 10 to the 13th meters per second squared, because it's only going to cover a small space, say about 5 centimeters between these two plates here. And in that time, it's going to have a huge jump in speed because these electrons aren't just sitting still. So, yeah, we're going to accelerate it up from about 2 times 10 to the 7th meters per second squared to about 2.2 over that distance. So we need a big acceleration for this problem. Other things we need, go ahead and pull out some attention-grabbing colors here. We need that equation for electric force. So force equals Q times E. We already have E. E is our green equation up above right here. So we can rewrite this then as maybe Q on an electron, which we know is 1.6 times 10 to the negative 19th coulombs, times E there from the electric field from parallel plates, and that's going to be the mass times the acceleration. And we're going to expand this out just a little bit. I'm going to pick a brand new color so we can rewrite it all together. It's going to be red. So we're going to have Q times 4. I'm going to stick the pi over there this time, K sigma. That takes care of this piece, and that's going to equal MA. So when it's all said and done, sigma is going to equal the mass times the acceleration divided by 4 pi k q. And it just so turns out that it's going to be approximately 2 nanocoulombs per meter squared after you plug everything in your calculator. So this is just one quick little application that you'll see in our problem sets as we move forward. We'll check out a few more as we work through this section, but again, pretty straightforward as long as you can find the electric field equation and you're familiar with the electric field. Adding the force, doesn't add that much extra work. So until next time, have a good one.